So we have here y prime plus 1 y prime plus py equals qy to the n. This is called Bernoulli's equation, yeah, because it's in the form of Bernoulli. So this is Bernoulli's equation. Yeah, so you can see just by comparing these two that p would be 1 over x and q would be 2x to the 3 halves. And n in this case would be half, because it's the power of y. You see that?
Oh, so, oh, wait a minute.
So now,
Wait, which is n the, is n?
N is this.
Oh, wait, no. So isn't it the highest, whatever the highest power of one is?
No, it's the coefficient, it's the exponent of the y after you write the equation in the standard form, like this.
So y plus something times y, or
It's
something
just
x times y.
yeah, it could be a function of x. It doesn't have to be, but it could be times y, and this is q, could be function of x. Doesn't have to be, but it could be times y to the n. So n is half. And to reduce Bernoulli's equation, you do a transformation. And that transformation entails the substitution of z equals y to the 1 minus n. So that means z equals y to the 1 minus half, which is equal y to the half. Okay. And now you do a transformation from z, from y to z. Okay. So with this, I could find out the derivative. So z prime would be 1 half. So you take the derivative now. 1 half y to the minus 1 half y prime, of course. Right? And so now you can solve for y prime and you plug it in there. So y prime will be 2z prime divided by y to the minus half, or multiplied by y to the half. And so now you replace y prime with this, 2z prime y to the half. You replace y, I could rewrite this as y equals z squared, right? You replace y with z squared. And obviously you replace y to the half with z. And so now we've got, so now the new differential equation becomes y prime is 2zy to the half plus 1 over x times y. We said y was z squared. Wait, this is z prime. Okay? And on the right hand side we have y squared, so this becomes 2x times y to the half. Y to the half is nothing but z. Okay. Now we have one y term left we need to get rid of. This is not supposed to be here because we're doing the transformation, but y to the half is just z.
Yeah.
So now we could remove this and we can put z here, so it becomes 2z prime z plus 1 over x z squared equals 2x z. And now we can divide this equation by z. So divide by, actually let's divide by 2z to put it in the standard form in one step. So when we do that, this becomes 2, or it becomes z prime plus 1 over x. When you divide here by 2z, you get a 2 here, and you get a z left. And when you divide by 2z here, you just get x. And now this is a linear equation in standard form. They already reduced to a linear equation. So that nonlinear term was eliminated by doing this transformation.
I'm still kind of confused as like what's the difference between the 1 over x, y, and or it doesn't matter which you designate p and which is q.
Yeah, it doesn't matter.
How do you know that? How do you know that the 1 over x is the p and the 2x to the 3/2 is the q?
I mean, honestly, I didn't have to know. I never used this as of yet. I didn't have to know. All I have to know is that the power of the nonlinear term. What's the nonlinear term in this differential equation? It's the y to the half.
Oh.
Needs to go away.
All right. It has to be the nonlinear one.
Yeah. But you do have to somewhat put it in the standard form, because it's the substitution requires the differential equation to be in the standard form.
I get it, because that's the whole point of the Bernoulli, is to get the dependent variable linear.
Mm-hmm.
All right. So it's not to turn a nonlinear equation into a linear equation.
Yeah, exactly. So now this becomes a straightforward one, yeah? And we can solve this now with an integrating factor. So the integrating factor method requires that we multiply this by mu. So we're going to call the integrating factor mu. So you solve for z, and then you plug it back in, you get your y. So now we have mu z prime plus 1 over 2x mu z equals mu x. And now we can work out the product rule from here backwards. So this is d over dx, and this has to be a function of x, of mu z to equal mu x. And now if I expand the product rule, I will get mu z prime plus mu prime times z equals mu x. And if I were to compare these two, it's easy to see that mu prime has to equal 1 over 2x mu. So d mu over dx has to equal 1 over 2x mu. And a simple separation of variables would yield du over mu equals dx over x, and there's a half here. And then if we integrate both sides, we would get ln mu equals 1/2 ln x, which is the same thing as ln x to the half, meaning mu is equal to x to the half. Bingo. So we found the integrating factor. So we take this integrating factor and we put it back in star. So substitute in star. So now we are doing the integrating factor method. And when we put it back in star, we get d over dx of x to the half times z equals x to the half times x. And now when we multiply this dx over, we get d x to the half times z. X times x to the half will give you x to the 3 halves dx. And now you can integrate this both sides, and by fundamental theorem of calculus, the integral would annihilate the derivative. And we would get x to the half times z equals, this is a straightforward integral, x to the 3 halves plus 1 will give you 5 halves, divided by 5 halves or multiplied by 2/5 plus c. And so which means z has to equal to divide by x to the half, 2/5. X to the 5 halves minus x to the half will give you x squared plus c x to the minus half. So this is z. No?
Yeah.
And we know that how z, and remember our original differential equation is in y, it's not in z, but we do know how they're related.
Yeah.
Y equals z squared. Y equals z squared from here.
Yeah.
Okay? From here. Double star. So substitute in double star. Y equals z squared. So that means y is just the square of this. Square of the answer. 2/5 x squared plus cx to the minus 1/2 all squared. uh, review here what happened. something wrong here. 2x instead of 2x, I copied 2x to the 3 halves, I copied 2x. That's not good. Yeah, there's a mistake. Yeah. So the mistake is here. This is supposed to be 3 halves, not x. Well, that changes things. So this is 3 halves. And when you divide by z, root 2z, you get x to the 3 halves. Okay, let's fix this. Shouldn't be too bad to fix it. So this is 3 halves, 3 halves, 3 halves. How about I go with a different color on all the mistakes here. Okay, so 3 halves. So technically this is um, um, okay, this shouldn't be affected, but this 3 halves will. So this will become x squared. And then when we integrate, this will become x cubed times 1/3. And then when we divide by x to the half, you're going to have left 5/2. And this is x to the 1/3. Okay. And this is x to the 5 halves. Yeah. Okay. Now it's working out. So x to the 5 halves here. And this is x to the minus 1/2. Okay, that should be fine. Okay, so yeah, just the power changes. So this should be the right answer. I just forgot to add a power for x on the right hand side. So this should do it, yeah? So this is solving this by reducing Bernoulli's equation and then using the integrating factor method. Do you get it, man?